Good afternoon, everyone. Today's video wasn't planned. I honestly thought I was done talking about 3I Atlas for a while. I'd already covered it extensively, and from the outside, it looked like the story should be winding down. The object made its close approach, past perihelion, and according to most official sources, it's already on its way out of the solar system. End of story. Except it isn't. Once again, 3I Atlas has forced itself back into the spotlight. Not because anyone wanted it to, but because it refuses to behave the way it's supposed to. As far as the mainstream scientific community is concerned, this object is no longer interesting. The assumption seems to be that it's already gone, already fading, already irrelevant. The sooner everyone stops talking about it, the better. And frankly, that attitude makes sense, if nothing unusual were happening. But something is happening. And the more data we collect, the more uncomfortable the situation becomes for anyone who wants this story to quietly disappear. So, once again, welcome back to the Angry Astronaut. Let's start with where 3I Atlas actually is right now. Despite what you may have heard, this object is not gone. It has not left the solar system. It has not stopped being observable. In fact, it won't reach Jupiter's Hill radius, its closest meaningful interaction with Jupiter, until sometime in March. It will remain inside the solar system for all of 2026. And, depending on how bright it stays, our most powerful telescopes may be able to track it well into next summer. That alone should already raise eyebrows. Because at this stage of its journey, 3I Atlas should be calming down. It is far past perihelion. It is moving farther and farther from the Sun. The energy-driving comet activity should be dropping rapidly. The coma should be shrinking. The tails should be weakening. That is what every known comet does. 3I Atlas is doing the opposite. Instead of fading, it is becoming more structured. Instead of simplifying, it is becoming more complex. And instead of settling into predictable behavior, it continues to throw curveballs. The biggest and most troubling of these is its anti-tail. Most comets have two normal tails, a dust tail and an ion tail. Both are pushed away from the Sun by radiation pressure and the solar wind. Some comets also show an anti-tail, which appears to point toward the Sun due to viewing geometry and particle behavior. But normally, an anti-tail is faint, short-lived, and much smaller than the main tails. That is not what we are seeing here. The anti-tail of 3I Atlas has been prominent from the beginning, but now it has become the dominant feature. It is brighter, longer, and more sharply defined than the main tail, and that is not something we have ever seen before. The latest Hubble observations make this impossible to ignore. On December 27th, Hubble captured a 172-second exposure of 3I Atlas using the WFC3 UVIS instrument at a wavelength of 0.5851 microns. The raw image by itself doesn't look particularly dramatic. That's normal. Raw telescope images often look unimpressive until they are processed. But once this image was run through a Larsen-Cecchinina rotational gradient filter, the situation changed completely. A clear double-jet structure appeared. We now have two processed images, one from December 12th and one from December 27th. And when you compare them side by side, the differences are striking. The brightness of the two jets changes significantly over just 15 days. One jet becomes brighter while the other fades. Their shapes shift. Their orientation subtly changes. Most importantly, the brightest jet is pointed toward the Sun. This is not an illusion. This is not a projection effect. This is a real, physical jet pushing directly into the solar wind, and doing so successfully. That alone should make anyone pause. This behavior didn't start recently. Hubble had already observed a strong sunward jet back on July 21, 2025, long before perihelion. That jet was about 10 times longer than it was wide, and it showed a wobble of roughly 7 degrees. That wobble matters. A 7-degree wobble tells us that the jet source is very close to the object's rotational pole. In other words, it came from a specific, stable region near one end of the nucleus. Now, here's where things stop making sense. After passing the Sun, 3I Atlas should have experienced a gravitational deflection of about 16 degrees. If its rotation axis stayed the same, then the original Sun-facing pole should now be on the night side, facing away from the Sun, which means the original anti-tail should no longer exist. But it does. Even stranger, the original jet direction now lines up with the weaker jet seen in December, while a new, stronger sunward jet appears on the opposite side of the nucleus. In simple terms, the object now looks like a mirror image of what it looked like before perihelion. That should not happen. There are two main ways to explain this. The first is that the jets come from opposite sides of the nucleus. That would mean the object's activity changed dramatically after perihelion. For a natural comet, you might argue that heat traveled from the day side to the night side, activating a second jet. But heat conduction through comet material is slow and weak. It does not produce strong, focused jets pointing directly at the Sun. In a technological scenario, however, this behavior becomes easier to explain. A sunward jet could act as protection against solar wind or coronal mass ejections, which have been unusually frequent recently. A secondary jet could help clear the path ahead or stabilize the object's movement. It's also important to note that the anti-tail is not very transparent. It reflects a lot of light and is harder to see through than typical comet dust. That suggests dense material, not a loose cloud of debris. The second explanation is that both jets come from the same sun-facing side, but are made of different particles. Large particles, around 10 microns in size, could form the massive anti-tail, while smaller particles get pushed away quickly by solar radiation and the solar wind, forming a weaker jet in the opposite direction. Particles this large can resist the solar wind for a long time, allowing the anti-tail to stretch hundreds of millions of kilometers. Smaller particles would reverse direction much faster. This explanation works on paper. The problem is that we have never seen anything like this before. Not once. The only way to know which explanation is correct is spectroscopy. By measuring the speeds of particles in both jets using large telescopes like Keck or the Very Large Telescope, we can determine how they are being launched. If particle speeds near the nucleus exceed 1 kilometer per second, solar heating alone cannot explain it. Natural outgassing tops out at around 500 meters per second. Anything faster suggests an additional energy source. There's more. Between December 12th and December 27th, the jets changed dramatically, in just 15 days. That kind of rapid change suggests either rotational wobble or extreme variability in the jet sources. Comparing multiple images taken during each 30-minute observation window can help determine which it is. Early signs point toward rotational wobble, because the brightness of one jet increases while the other decreases in a predictable pattern. This fits with earlier observations. Back in July, 3I Atlas showed a repeating brightness cycle with a period of about 16 hours. It brightened and dimmed regularly as it rotated. As mass continues to be lost, that rotation period may have changed slightly, possibly down to around 15.5 hours or less. Avi Loeb's team is currently analyzing the latest data to check for this. Now let's talk about dust. The particles forming the anti-tail appear to be about 10 microns in size, much larger than typical comet dust. Particles this big can push against the solar wind, but not forever. How far they travel tells us how big they can be. Each particle has a mass of roughly 10 to the minus 8 grams. That sounds tiny, but there are vast numbers of them. By measuring how much sunlight they reflect, we can estimate how much light comes from the dust versus the nucleus itself. From this, Avi Loeb estimates a minimum nucleus diameter of about 2 kilometers, assuming all light is reflected. If the nucleus is producing its own light, then the dust could be acting as a reflective shield, hiding a smaller core. In that case, the nucleus might be closer to 1.4 kilometers in diameter. Either way, these are minimum sizes, and the dust cloud itself is close to opaque. A camera with very high resolution wouldn't see a clean, solid object. It would see a blurry, glowing cloud. 3I Atlas is effectively hiding whatever is at its center. So, what do these Hubble images really tell us? They tell us this object isn't finished surprising us. Even as it moves outward, its behavior keeps changing. The anti-tail dominates. The jets shift. The brightness fluctuates. The color changes. And we need to keep watching it for as long as we possibly can. Because one thing is clear, this is not behaving like a normal comet. So, is it natural? Possibly. I'm not saying it must be artificial, but I also don't think it's reasonable to say it's probably natural, given everything we're seeing. The trajectory alone would be extremely useful for a probe passing through the solar system, or for an object designed to interact with multiple planets and moons. Could all of this be coincidence? Yes, but the more coincidences you stack together, the less convincing that explanation becomes. The long-lived sunward jet, the tightly focused structure, the massive anti-tail fighting the solar wind, the ongoing activity far past perihelion. None of this feels ordinary, and yet very few scientists are willing to even consider a technological explanation. We constantly ask where extraterrestrial civilizations are. Maybe the better question is why we refuse to recognize them. If even a small fraction of unexplained phenomena are artificial, then the so-called Fermi paradox disappears. Perhaps they don't contact us because we aren't important. Perhaps they communicate in ways we don't understand. Or perhaps the universe really is a dark forest where advanced civilizations stay silent to survive. If that's true, then broadcasting our presence for over a century may not have been wise. I truly hope that isn't the case. Thanks for listening. If you found this analysis valuable, consider supporting the channel and keeping the discussion going. More observations are coming. More data will arrive. And 3I Atlas will continue to challenge what we think we know. Until next time, stay curious.